Hey, Sienna, how's it going there?
Good. How are you?
Oh, doing pretty good. How's the studying coming along?
Good.
Good, good, good. Okay. Now, did you get a chance to look at some of those problems that we were looking at last time or to review them?
Yeah, I reviewed a couple of them
Okay.
last night.
You feeling better about it?
Yeah.
Perfect. Okay.
Let
Now,
me share the screen.
we put the link over
Oh,
there. You go right
um,
ahead.
okay.
Okay, so we're going to talk a little about limits here today. Um, what are you struggling the most with limits?
Um, I guess I'm not really familiar with quadratic equations when it comes to these problems. And also, I don't know if it's the same, but like I'm looking at a problem right here about like a rational um equation, and I was like unsure how to choose epsilon or delta, sorry, like when you do like the minimum and it's like two numbers. I wasn't sure like what exact like values to choose, sorry, to choose for those two things.
Hmm.
But I'm not familiar with these types of problems, the quadratics where like maybe something is different.
Okay. Let's take
That's
it
where I'm.
back a little bit. Let's see if we go back and look at the limit as x approaches 2. And you're looking at 3x plus 1. Now, back in calculus 1, when we took that class, we see that this is continuous functions, polynomial. Take it, just drop it in, and you see limits can be 7.
Mhm.
That's not a big deal. But
Yeah.
can you actually prove it? That's what we're really after. So, in order to go about your limits, you have to look at necessity and sufficiency closeness, whatever that means.
Mhm.
And that's where that delta and the epsilon comes into play. What is the actual definition, the delta epsilon argument definition of a limit?
So for every epsilon greater than zero, there exists a delta greater than zero such that um, zero is less than the x value, in this case two. Oh no, sorry, not two, not eight. I mean x, x or absolute value of x minus the two um, in the problem, and it's less than delta, which I don't. The arrow means implies, right?
Mm-hmm.
Yeah, it implies the absolute value of the function minus the limit is less than epsilon.
Right. Now, here we have a universal and a existential statement where
Mhm.
we're saying for anything you pick out there, I can find something, find the
Yeah.
delta. So really in these problems, your objective is really figure out what in the world's a delta because someone's going to say, hey, look, here's an epsilon, work with it, do your magic with it. And you do your magic with it and you say, abracadabra, here's a delta. Well,
Mhm.
you could say abracadabra, just makes it more fun. But so how would you approach this in terms of a linear function? What's your starting spot?
Maybe starting with the right side, kind of like filling in those blanks.
Whenever
So,
you're looking at these kind of situations, you kind of want to pretty much do a little bit of reverse engineering. A lot of times the proofs are going to start off by saying you're given epsilon greater than 0, or you might preface it and say, let epsilon be greater than 0 be given. It doesn't really matter how you state it. Just make sure that epsilon is an arbitrary universal statement. That's the key. So look right here. Here's your function. you're going to say f of x plus 1 minus the limit. And if you were to just tinker around with this a little bit, what you would see is you would have 3x plus 1 minus 7, so minus 6. Factor out the 3. Apply the definition, the properties of absolute value. And the absolute value of 3 is just going to be 3. So in other words, 3 times x minus 2 is going to correspond to f minus L.
Yeah.
What is that right there telling us?
That 3 absolute value x minus 2 also is less than epsilon.
And that piece is right there. See, here we know that this is going to be given.
Oh, I see. Okay.
Our objective, again, is we have a universal statement on epsilon. I'm not worried about epsilon at all.
Okay.
I'm worried about delta. Because for any epsilon out there, I can always find some delta corresponding to that epsilon so that it works. Mm-hmm. So if I know that this is going to be less than epsilon, here's my delta. Divide everything by 3. And that's what I want to set delta equal to.
Okay.
Okay. Does that make sense?
Yes.
Okay. Make sure that logic makes sense because that's what's going to help you get through to the more complicated ones.
Yeah.
Okay. Now, once you have all this, you basically brush this off to the side and pretend like you don't see it. But every so often, you're going to come over here and you're just going to peek at it and use it to help you construct a proof. Okay. Here's how you do this. You would say let epsilon be greater than 0 be given, or something along those lines. Just once again, just make sure it's arbitrary. Mm-hmm. And we're going to let, here's the existential statement come into play now, let delta be a particular arbitrary element hinged to epsilon. We're going to set this equal to this. And we're going to consider, we're going to be considering this open ball, this interval, x minus 2. Whenever you look at the absolute value, you're looking at some kind of open ball. If you write it in 2D, if you write it in 1D, you're looking at some kind of interval. And that's the region you want to look at. You don't want to look outside of it, just inside there. And the distance you're going to be going is a distance of delta to the left or to the right. So you want to consider the metric, the distance, x minus 2 less than delta over 3. Or sorry, delta. Now, we know from above that delta is going to correspond to epsilon over 3. So take it and drop it in. And the question is, if I have this, does it mean I also have this? See, when I look at the conditional statement, I have P, I have Q. The premise is true. I'm saying that this is given. And in order for the conditional statement to be true, I need Q to be true. Because I can't have true implies falsehood and expect to get a truthful statement out of it. Mm-hmm. So to get that tautology we're after, I got to make sure that, yeah, this metric, F minus L, is less than epsilon. That's the goal. So from here, once again, you can peek, see what happens over here on the side. and use it to help you to reverse engineer it if you need to. So I might want to say something along the lines of, now consider the following, or something along those lines. We'll have x minus 2 less than epsilon over 3. Let's multiply both sides by 3. Then let's go ahead and absorb the 3 inside using properties again of absolute value. We'll have 3x minus 6. And my goal, my direction, I'm trying to say f minus L. I know what the f function is. That's going to correspond again to the 3x minus 1. I know L's going to have to be 7. So it's my job now to figure out some way, somehow, to find these pieces inside of here. And I get the clue of how to do that when I come back and I look at how we reverse engineered it to figure out the delta. I look at it and say, okay, I got that piece, I got that piece, I got that piece. Oh, I just got to do that.
Yeah.
Okay, so we take it, zip it back tight again, repackage it, and I can say this. And we have the function minus L is less than epsilon. And I just showed for any epsilon out there, doesn't matter which one you pick, just let it be given. You search high, you search low, whatever it is. I can find some delta, and the delta that I'm going to select is this delta. Why am I going to select this one? Because I know it's going to work. And all I don't need an arbitrary, I need an existential on delta. And I'm going to pick it in a way so that when I look at this region on the interval, I'm just focusing right there. I see that when I get close enough, up top is closer still. Here's my epsilon. There's my delta distance. And then from here, it's just a matter of algebraically manipulating it to show that, yeah, I do have f minus L. Because when we look at the conditional statement again, the sheer definition, I have to show that if I have P, it implies I have Q. You do that, you've just shown the limit. Okay, take a moment. I want to see if that makes sense.
Okay. So this would be the whole proof, basically?
Pretty much. Now, you do have to clean up a little bit more to articulate it a little bit better.
Yeah.
But that's all the pieces that you need to formalize a good working proof.
Okay.
Okay, so tell me the steps. How did I go about proving this?
Okay.
What's the
well,
first thing I did?
Okay, first thing, finding a way to say that it's given that epsilon is greater than 0, or like let epsilon be greater than 0 be
Good.
given.
Make that your step 1 in your checklist you're doing right now on your list.
Okay. And then, so the point of this section, I guess, is like reverse engineering it first for myself.
Right.
And then in that, I take the function minus the limit, which in this case was parentheses 3x plus 1 in absolute value altogether, minus 7. Then I'm kind of like solving it like 3x minus 6, and then taking out 3 to kind of isolate the x minus 2, and then finding or I mean right there recognizing that it's the f minus L less than epsilon. It's just 3 absolute value x minus 2, and then finding my my delta by noticing that like by dividing the 3 over x minus the absolute value of x minus 2 is less than epsilon over 3, and then kind of going back to that statement, recognizing that uh, the x minus 2 less than epsilon over 3 is also like corresponding to this part of the statement. So then assigning delta to epsilon over 3. And then finally getting into the proof. Again, like also let epsilon be greater than 0 be given. And then also saying let delta be epsilon over 3. And then considering that part of the statement, x minus 2 less than delta, and also like the now, like including that part of the statement, and then also the what the delta I've assigned is, which is this part. Then you're going into like considering the following. So we start off where we ended basically. So the 3 absolute value of x minus 2 less than epsilon, and then kind of going backwards now. And I'm absorbing the 3 back into the absolute value, and then I distribute the 3. And then here I'm like seeing, or here I'd go back this part. I'd go back and look at this section, and recognizing that that also can be like represented as the parentheses 3x plus 1.
Use it as a guide.
Yeah, minus 7. And then recognizing that that is literally the f of x minus L.
Right.
Yeah.
That's it. So again, epsilon, that's going to be given. You can just make that your opening sentence pretty much whenever you're doing these proofs. The next thing you're going to be shooting for is just push the proof to the side, get some scratch paper, and just do some reverse engineering and say, okay, what do I need for delta? That's what you need. As soon as you figure out how close, how small that interval, the open ball, the x minus 2 in this case, you're going to then use that and then get to the f minus L. You have to show the conditional statements true to show the limit.
Okay.
Okay, now what I'm going to do, I'm going to push this to the side, and I'm going to put another one up here for you, just for you to practice. And let's say we're looking at the limit, 5x plus 3, x approaches 2. And once again, calculus 1 tells us, just take it, drop it in, you get a value of 13. But now we actually want to prove it.
Yeah.
Okay, so I'm going to give you a few minutes there. I want you to see if you could actually develop the proof for this limit.
Okay.
So, yeah, that's pretty much the gist of it. You got it. Again, epsilon's going to be given, and you're going to make a choice. And the choice you're making here, a lot of times when you're reading proofs, like, where in the world did that person come up with this? Well, they did a lot of work to the side they're not showing you, and that's where you did that reverse engineering. It's right there. Then you use this and say, okay, we're just going to select it so within this region. The only thing is it's not a comma, but that's fine. Just replace the delta with what it is and make a beeline, reverse engineer it, get down through as fast as you possibly can. Because now we have P, we have Q, and we just show that the truth of P doesn't imply the truth of Q. Okay. Great job.
Thank you.
Okay, now when you take it to the next level, we start looking at quadratics. It gets a little bit more complicated, but for the most part, it's going to have the same ideas again, because you're using the exact same definition. You're still looking at the limit definition. You're still trying to show that P does imply Q. Okay, so, okay, remind me again, what was the the definition for a limit.
So let epsilon be greater than 0, such that, or yeah, sorry, for all epsilon
Mhm.
greater than 0, there exists a delta greater than 0, such that x minus 2, or x minus a in this case, is less than delta, which implies the absolute value of f of x minus L is less than epsilon.
Good. So we're still doing the same thing. Here gives P, here's your Q, and you got to figure out a delta that's hinged to the arbitrary universal epsilon out there. So it's particular, but once again, it's particular based upon the arbitrary. So let's just kind of play around with it for a moment. If I have the f minus L, I'm going to have f of x minus L, and f of x is going to be x squared, and L is going to be 4. And I need this to be less than epsilon. Now, if you look at this, what do you see with x squared minus 4?
It also can be written as x minus 2, x plus 2.
Right. Now, this right here, it's real obvious when you see the difference of squares so you can factor it.
Mm-hmm.
And this oftentimes in these problems, this is the key. Because whenever you apply the properties of absolute value, the property that says if you take a product, you can split it up like this.
Mm-hmm.
What's this?
Oh, it's in our statement.
That's exactly right. It's right there. So we got this piece of the puzzle. We just got to figure out how to make the things come together. Okay. Now, once again, we are looking at some kind of open ball, some kind of interval. Going at 2, we might go in this direction, some kind of delta. Now, as I get closer and closer to 2, maybe I'm at a value of 5 to begin with. If I say 5 minus 2, that's going to get me a measurement of 3. I'm 3 units away. In order to get close to 2, would it make sense, or am I just completely wrong and it doesn't make sense? Or to say that x plus 2, or excuse me, x minus 2 has to be less than 1 eventually. If I want to get to 2.
Yes. Oh, sorry, I can't hear you.
Oh, there, sorry. Yeah, it makes complete sense, doesn't it? Because if I go 1 unit away, I know I'm over here at 3, and if I'm less than, I know I'm somewhere inside of here, or maybe over on the left-hand side. Okay, so here's what we're going to do. We know that eventually this is going to be the case. So let's go ahead and just say, suppose this is the case. Suppose that we're going to get small enough. And again, we got to make sure we have this necessity and sufficiency of closeness. So eventually this has to be the case. Otherwise, the limit doesn't exist.
Mm-hmm. And are we choosing 1 because it's just easy to work with?
That's exactly right.
Okay.
I could have chose 2 if I wanted to. I could have chosen 5. It's typically it's customary because it's just easy to work with. So take the inequality and you're going to open it up. Add 2 to both sides. Add 2 to both sides. There we go. And the problematic piece that we have is really this piece right there. But what if I took this inequality and add 2 to everything? that would then say that x plus 2 is bounded above by 5 and below by 3. And you know what we just did? We found a bound. In fact, we found an upper bound. So the magnitude of x plus 2, remember, I'm looking at the center, it's really over at -2, or as I'm looking around the open ball, it's no bigger than 5. So based upon the assumption, if we assume that we're looking at that region, then we can safely conclude that the magnitude of x plus 2 is less than 5. Okay, take a moment, see if that makes sense to you.
These are bounds for delta, right? Or no?
We're getting there.
Oh, okay.
This is how you're going to find it when you're looking at in terms of squares.
Okay, and then so if we assume basically that we're gonna get so close to 2 that we're gonna be 1 away from it, or it's gonna be less than 1 away, then that also means that there is an upper bound of x plus 2, like that is less than 5. Is that what we're saying?
It's saying as I get closer and closer to the value of 2,
Okay.
then I know that I'm going to have this eventually.
Okay.
Now, the reason why I'm after this, because again, I want to look at f minus L. My goal is to show that this is less than epsilon. That's the same goal as in terms of linear, but because it is quadratic, it adds an extra layer of complexity you have to contend with as you're trying to figure out the delta. Okay, so you might want to write this down. F minus L, same thing, but you're going to try to find the x minus 2, this x minus a. You're going to try to find it some way, somehow in this step. Then the next thing is you have to do something with the x plus 2. You just got to. You got to figure out some way to bound it. And that's why we set it less than 1, because it makes it easy. And I know eventually it's got to be small enough. Otherwise, if x minus 2, if this is always bigger than 1, you're never approaching 2.
Yeah.
So I know eventually it's going to be less than 1. And like I said, you can say 4 if you want. You can say 7 if you want. It's just 1 makes it easy. Okay, so that's part of that scratch work. And we'll just push that off to the side now. Now, after you figure out what's going on here in this case, this is where I want to start looking at what I'm going to need here for delta. So again, we're going to let epsilon greater than 0 be given some arbitrary value, and I'm going to set, and let's take a closer look at it. Here's my f minus L. We found this out. And when I look over here, I know that always, 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 the x plus 2 is bound above by 5. And what I really want is I want the x minus 2 less than some delta. That's my goal. So what if I make delta equal to epsilon over 5. If I do that, and I look at what's happening here within this region,
Oh, we get, is it epsilon over 5 times 5?
and you get your epsilon.
Okay.
Okay, now let me pause again because this gets a little bit more complicated because of the extra layer of complexity. It's a little bit more mental gymnastics. Does it all make sense how we got here so far?
I am just confused as to how we know. Maybe I just need to talk through it. But how do we know that this is in fact bigger than these two?
Well, that's a really good question. This is only going to be the case whenever I have that right there. If I don't have this, then I may not have that. But I do know eventually I'm getting closer and closer to that value, and eventually it is going to be less than 1.
Yeah.
Now, really, to get the delta, the next piece to this puzzle, since I'm making this assumption, I got to do one more piece. I got to say, let, and we're going to define delta as a minimum value. And I think that's going to address the question you had there.
Mhm.
Because we're going to break this from the cases. If that's going to be the minimum,
Mhm.
okay, then I know whenever I'm looking at x minus 2 delta, and delta is 1 because it's the minimum, this is going to work. Now, in the event when it's epsilon, and maybe that's going to be something like, I don't know, 10 or something. Or since it's arbitrary, it might be something like 1 over 10. It's just something that's going to be non-negative. But if I make the choice where I make delta equal to the epsilon over 5, and if this is the absolute min, I know that I will have this right there then. So it's kind of like case 1, case 2, minimum if it's 1, minimum if it's epsilon over 5. And what you want to do is pick the smallest of the two cases, the smallest one. Because I need that distance to get shorter and narrower and closer.
Yeah.
Okay. Now, with all that, we still haven't got the proof, but we got the direction as to what we need to do with this. We have figured out how to choose delta, and that's the important part again in this problem. Okay, so let's actually prove it now. So let epsilon be greater than 0 be given. And you can say define, you can say let, something along those lines. Let delta correspond to the minimum value, 1 epsilon over 5. And consider the metric, the bound, the interval we'll look at x minus 2 is less than delta. Okay, now what that does mean is I got two cases to work with. I got the case that maybe this delta, maybe that is 1. That's possible. And maybe I got the case where delta is this epsilon over 5. That's also entirely possible.
Mhm.
here, if I have x minus 2 and if it's less than 1, I could take this inequality and multiply both sides by x plus 2. And I know beyond a shadow of a doubt that whenever I have x minus 2 is less than 1, x plus 2, that's going to have to be less than 5, based upon the work that we did a moment ago.
Yeah.
Now, delta, this is case 1, that's the minimum value, correct?
Yeah.
Okay, that's important. Since delta is 1 and it is the minimum, what that means is the other value is bigger. Epsilon is bigger than 5. Link it in. And this piece back there, if we were to do some algebra, pull it back together, use the properties of absolute value, difference of squares. What did we just show? Here's P again. There's Q.
Mm-hmm. We proved
And
Q to be true.
we proved part of it because we were using a minimum value, so we have to look at cases.
Oh, okay.
So what we just shown is the limit definition does hold. We do get a true value when delta is equal to 1. Okay, that's case 1. Case 2. Suppose that delta is epsilon over 5. Now, once again, because delta is selecting the smallest value, the minimum value between 1 and epsilon over 5, what this immediately means is it means that. So epsilon has to be less than 5 now in this case. Whereas beforehand, epsilon was greater than 5.
Oh, okay.
Okay, so we'll have our x minus 2 is less than delta. This is what we're starting off with. This is kind of given, but delta is going to be epsilon over 5. Let's do the same thing. Let's go ahead and multiply both sides by x plus 2. Now, what do we know about this? Well, delta, that's the smallest value of epsilon over 5, and it's less than 1. So, without really stating it, it's being implied that x minus 2 is less than 1. But wait a second. Wait a second. Didn't we discover a moment ago that when x minus 2 is less than 1, that means that's less than 5? Absolutely. Drop that information down here and keep pushing through the inequality. So you might want to say something like recall, and then you can say so or thus, or Therefore, something along those lines. What's bigger than an x plus 2? How about a 5? And when we push on the left-hand side, again, put it together using the properties of absolute value. We get this, which is that. And in case 2, when you made this assumption, the P, we eventually got to the conclusion, the Q, as being true. So, irregardless if it's case 1 or case 2, we just show that x squared, whenever you're looking at the limit, as x approaches 2, it will be a value of 4. Okay, let me give you a moment there. I want to see if that makes sense.
Would it be like, I'm looking at this section here. So I know we found this, like the P, we found it like with the work that we were doing before. I remember when we were doing like when we found the bound, or we eventually like we said that eventually that x, the absolute value of x minus 2 will be smaller than 1 as we're approaching 2, which makes sense. And then we found the upper bound by kind of manipulating that inequality and finding that that also means that the upper bound would be that x plus 2 is less than 5. So looking at this statement, if I remember those things, I'm seeing that here we know that this is less, or we know that basically from this information from P, we know that the one on the right is less than 1 and the one on the left is less than 5, based off what we found. So if we were to multiply those two things, they would be less than, I don't know, like for example, 4.5. Like if you multiply those two things, you get 2, which is less than 5 here. And then that's when we say this. Am I going about that thinking wrong?
I think so. Think of it like right here with inequality, we have circle and P. Multiply both sides by x plus 2.
Okay.
And then after you multiply both sides, what was bigger than x plus 2 in magnitude?
5.
5. See, a lot of times when you're doing these delta epsilon arguments too, you're chaining up a bunch of inequalities so you can get to the epsilon or the delta, get to the piece you need.
So I shouldn't think like that because this greater, like less than 5 is applying to this part, the other side of the inequality that I'm multiplying.
Yeah.
Oh, okay.
I think you'd be better off if you thought more like that. Yeah.
Okay. All right. Okay. I just wanted to correct my thinking.
Okay.
Because then if I'm going through a problem, it will, if I could look at it the right way, then I feel like I would be closer to getting the answer. Like,
right.
Just from multiplying the other part of the difference of squares. And then recognizing that, oh, wait, I see on the right side that x plus 2 is the absolute value of x plus 2 is there. I also know that that is less than 5 based off what I had just found in the scratch work. Okay. Okay, that makes more sense.
Okay, now, does the second case make sense?
So I'm looking at this inequality. If I'm thinking about like that bubble, where we're looking at like the values that are near 2, in this case, I know that eventually like we'll get so close that the delta value will be less than 1. So just knowing that the epsilon over 5 is also less than 1,
Well,
I think that is what's tripping me up.
kind of in the first case, we're saying we're looking at when it's less than one. No, epsilon, it can be 1,000. That's just way out here.
Mhm.
I don't care about that. I'm only focused on when it's less than one,
I
looking at
see.
that interval. Now, when delta eventually starts getting smaller and smaller and smaller, we're going to hit that threshold and get smaller still. That's okay. It's pretty small. I mean, still inside that less than one, but it's kind of like I refined the measurement, so it's better still. So the whole entire one, like, get rid of it. Look at the smaller one instead.
Okay. So, okay, when I read it, I read this as like, okay, I only want to care about when epsilon over 5 is less than 1, which then implies that based off, I multiply 5 on both sides, then I also get that this is implied by this statement.
Mm-hmm. Multiply
Okay.
both sides by 5.
Yeah. And then, so here I'm doing the same thing where I'm multiplying both sides by x plus 2,
Mm-hmm.
or that's
Mm-hmm.
probably what it's 2.
It's non-negative quantity, so you don't have to worry about flipping the inequality.
Yeah.
Just multiply it through.
And then recall that x minus 2 is less than delta based off the statement, right? The statement. And then when I'm reading this, when I see the it's also less than 1, is that because is that kind of like the same sentiment here where I'm like I only care about what's below or what's within 1?
Yeah, that's exactly what that is, because delta is epsilon over 5, and epsilon over 5 is less than 1 because we're taking the minimum value.
Okay,
So I
okay.
know it's going to be less than this. And the reason why I want to hinge this to say it's less than 1, because I know what happens for the x plus 2. It's always bounded by 5.
Mm. So or recalling the bounds that we found.
That's right. That's scratch work we did earlier.
Okay, so then here are we doing the same thing? Like we're multiplying both sides by x plus 2.
Mm-hmm.
Okay, and then mm, is this kind of like the aha moment? Like the it's less than epsilon.
Mm-hmm.
So
Yeah,
I
that's
see.
definitely the aha moment.
Okay. 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 I think it's starting to click.
Does it make sense to you, Siani?
Yeah.
Good. Okay, so describe to me real fast how you're going to approach these kind of problems when you look at quadratics.
Okay. So when I'm looking at like a question that has to do with the limit, first I'm gonna like write out the existential statement. So like for all epsilon greater than, I mean less than 0, there exists a delta greater than 0, such that uh the x minus a is less than delta, which implies that the absolute value of the function minus the limit is less than epsilon. And then, so first thing that I'm gonna do is look at that f of x minus l, um, and kind of manipulate or not manipulate, but kind of substitute like the x squared minus the 4, or is that the problem? Yeah, and I'm finding that like pulling it out and seeing that it's like a difference of squares, and all of that is less than epsilon based off the statement. And then we're kind of looking at or now rewriting it based off like the um absolute value rule, which we can like split them up. So we can say that the absolute value of x minus 2 can be multiplied by the absolute value of x plus 2. Then here, I'm kind of recognizing that eventually, based off the statement x minus 2 is less than delta, that will eventually be less than 1. It's a convenient number that I can choose. And then manipulating that inequality, we know that that's the lower bound. But manipulating it, then trying to get to that other part of the bound, which is x plus 2, we find that the upper bound is 5. So if we assume that lower bound, then the upper bound is also existent. And then so if we let epsilon be greater than 0, we can set delta equal to epsilon over 5, which is the upper bound. And then looking at the f minus L, the absolute value of function minus L, I'm multiplying both sides by x minus 2, and then I also multiply that right side by 5, and then finding out that the delta is equal to the minimum of that lower bound, which is 1, comma that upper bound, which is epsilon over 5. And then in terms of the proof, we're kind of going from, it's kind of going backwards to what we just did. So we say that epsilon is greater than 0, that is given, and then we let that delta value of minimum of 1 over epsilon over 5. And then we consider that part of the statement where the x minus 2 is less than delta. And then we think about the cases that we have for that minimum. So we think of like the delta as for 1, and then the delta as epsilon over 5. So when we think of that first value, we like have the x minus 2 is less than 1. We multiply both sides by x plus 2, the absolute value of x plus 2. And then we recognize, oh my God, I see the upper bound. That's also less than 5. And so since the delta is 1, that implies that that is less than the delta over 5. And that also means that the epsilon is greater than 5. Yeah, because it's just kind of continuing that first line here. And then this case, we basically found that the epsilon is greater than 5 because the 5 is greater than the x plus 2. And then from there, I kind of reverse it. So I absorb both of the absolute values into 1. Then I go back to like my scratch work and I see that, or rewrite it to be what it is, like x squared minus 4. Therefore, proving that it's less than epsilon, which is proving the first part of our Q statement, the first part of that minimum. Then we kind of do the same thing for the second case. We choose delta is epsilon over 5. And then here we note that it's less than 1, meaning when I manipulate that, I can say that 5 is greater than epsilon. And then I start off with the statement like I did before, or yeah, the x minus, in this case, x minus 2 is also less than epsilon over 5. Then I multiply both sides by x plus 2. And then going back to what I previously found, I know that x minus 2 is less than delta, and that we said also, like from the statement before, that eventually x minus 2 will be less than 1. So then that also recalling that when we multiply both sides by the x plus 2, It's also saying that it's epsilon over 5 and multiplying that by 5. That's kind of the aha moment where I can like be like, notice that I'm so close to getting the epsilon, just multiplying the 5 is will get me there. And then um at the end, tying it all back into what the f of x minus L, which is the x squared minus 4, is less than epsilon, then we're proving that other part of the Q statement um, for the epsilon over 5. Yeah.
Good, good. Now, let's just take a quick look at this one. Your number 2. You see where it has quadratic?
Yeah.
So what we're going to do again is look at f minus L. And when I look at this, you see the x approaching 1.
Mm-hmm.
That's kind of giving you the clue of how this is probably going to factor. Let's just see if that works. 2x squared minus 2x. And would you look at that? 3x minus 3. So you're going to do pretty much the exact same thing. Instead of bounding the x plus 2, try considering bounding to 2x plus 3. And set up the argument in terms of a minimum. Maybe use 1 and delta equals epsilon over 5 over 3, whatever it's going to correspond to, and get this cranking the way it needs to crank.
Okay.
Okay, so try that later on here today and use the example we just worked on to help guide you through it.
Okay. Perfect.
Good. Well, how are you feeling about the limits?
Better.
Good. Okay, so tomorrow when we meet up, what would you like to talk about then?
Could we talk about the next question on the review?
Which one was that one?
Question 3.
Was that on relations or?
Yeah, I can check real quick.
Okay.
Yeah, it's talking about sets and surjection and injection.
Okay, injective and surjective sets.
Mhm.
Okay, yeah, sounds good. Oh yeah, we'll definitely take a look at it there. But keep practicing this, and if you need any help in the meantime, let me know. Otherwise, I'll see you tomorrow.
All right. Thank you so much.
All right, take care.
You too. Bye.